At the end of this lesson, you will be able to factor a polynomial using the difference of two perfect squares. You will be able to differentiate between when to use the GCF method or the dots method to factor a polynomial. First, review something that we should already know. It says, express the product of 3x plus 2 and 3x minus 2 as an expression in standard form. So product means I need to multiply. So if I want to multiply binomial with binomial, I should use parentheses to first remind someone or indicate that this is a binomial times another binomial. Now, when we multiply binomials, we double distribute. So this 3x wants to distribute to 3x minus 2. So I like to break apart this binomial and show it wants to distribute to the 3x minus 2. And then this positive 2 also wants to distribute, so plus 2 wants to distribute to 3x minus 2. Now when I multiply, it turns out we end up with 3x times 3x is 9x squared. 3x times negative 2 is negative 6x plus 6x, and then minus 4. Our final answer, after combining like terms, turns out to be just 9x squared minus 4, because positive 6x combined with negative 6x ends up being 0. So this is our final answer in standard form. I've already combined like terms, highest exponent down to no exponent. Okay, next up we want to list our perfect squares. Today's lesson is going to require our review of our perfect squares. So, for example, 1 squared is 1. We're going to list, this should say our first 15 perfect squares. Let's do 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. You should continue until you've listed all 15. So pause the video now, and then when you press play, all of them should appear. Okay, I have all 15 perfect squares listed, but I'm going to circle the numbers that are actually the perfect squares. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and 225. All of these numbers should stand out. You should recognize them as perfect squares, whether they are within a problem or you are being drawn to a square root or perfect square. Next, we are reminded that perfect squares can also include monomials with variables. So for example, a monomial, meaning only one term, that contains variables, such as x squared. That is a perfect square because x times x gives me x squared. Or y to the fourth, because y squared times y squared would give me y to the fourth. Or 36x squared. This would be 6x times 6x gives us 36x squared. I could also have 25x squared y to the fourth, and so on. So now let's use our knowledge of perfect squares to simplify the following square roots. The square root of 64 we know is 8. The square root of y squared would be just y. Y times y is y squared. Well, the square root of 144 is 12, and the square root of x squared is x. This is true. The square root of 144 x squared is 12x because 12x times 12x gives us 144x squared. Alright, the next step is r squared s squared. So this would be rs because rs times rs would be r squared s squared, or rs squared. Okay. Next one, square root of x to the fourth would be x squared, and the square root of 196 is 14, And then we have a squared would be a, and the square root of b to the fourth would be b squared. The purpose of all of this review is to get to our next factoring method. The next method of factoring is called dots. It stands for the difference of two squares. So when we say squares, I really mean perfect squares. So the difference of two perfect squares, except it doesn't quite fit in the acronym DOTS. So there are three requirements. It must always be a binomial, or have two terms only. So as you can see, term 1, term 2. Both terms must be perfect squares, must be numbers or monomials that are in those lists from above. So this would be a perfect square because 9 and x squared are both perfect squares, and so is 4. And last, they must have a subtraction sign. This is the difference. Difference means subtract of, and then these two things here, these two terms, are perfect squares. The difference of two perfect squares. Two squares. Alright, so now let's see what we do to reverse it. But first, let's make sure you can find other expressions that can be factored using this method. Because this is a binomial that has subtraction of a perfect square and a perfect square, this is an example of a polynomial that we can use dots for. I'd like for you to pause the video, circle all of the ones you can find, and then press play to check your answers. Only circle expressions that fit these three requirements. They must be binomials, perfect squares, and subtraction in between. So now pause the video and check your answers. Okay, difference of two perfect squares. This one is not the difference, so it's out. It says the difference of two perfect squares, the difference of two perfect squares, difference of two perfect squares, and so on. This one has the difference. It is a binomial, but these are not perfect squares. This is a trinomial, so that's out right away. It needs to be a binomial, which this is, and it has a perfect square here, but not here. Both terms need to be a perfect square. Okay, our steps for actually using the dots method. First, we need to determine the square root of each term. So we would need to know the square root of each term. The square root of x squared, for example, would be x, and the square root of 25 would be 5. So we know the we know the square root of each term. And then on our paper, we create two factors that are blank. So you would always write just these parentheses with a plus, and then parentheses with a minus. One positive, one negative. Does not matter what order. And then to figure out what would go here and here, we take the square root of each term, as you can see. So fill this into your notes. First term, second term, first term, second term. And if I were to answer the example we see up here, I would set up my parentheses with my plus and my minus, and it would be blank. But then I would know that the square root of my first term here is just x. So x would go here, x would go here, because it's the square root of the first term. And then for the second term, the square root of 25 is 5. So this would be my answer. To prove that this is true, I can multiply my answer to see if it works. I propose that x plus 5 times x minus 5 should give us x squared minus 25. Let's check. If I take this x and I want to distribute it to this binomial, I have this, so x minus 5, and then I have positive 5 that wants to distribute to x minus 5. And what happens is I end up with x squared minus 5x plus 5x minus 25. And when I combine my terms, the middle terms combine to 0, and I end up with x squared minus 25. Okay, so as we get further through these, they should move quicker and quicker. First step is to confirm that it's dots, the difference of a perfect square term and a perfect square term. So I would start out with my empty sets of parentheses. And then I need to take the square root of this first term, and I get 3x and 3x, followed by the square root of my second term, which is 2. So my final answer is that 9x squared minus 4 is actually the answer of this product that I see here. This binomial times the other binomial. And if we revisit, back at the beginning, our first problem was exactly that. We started with our answer this time, and we found that this is where it began. And that matches what we've done here. The answer came from this. So let's make our other predictions. This one we would have blank, blank, a plus and a minus, always. That's the only way the middle term will cancel. So now I have the square root of x squared is x and x. The square root of 36 is 6 and 6. I'd like to try maybe this one next, number 7. So now I have my same rules. I have my plus, my minus. The square root of 81b squared would be 9b, because 9b times 9b would give me 81b squared. And the square root of 1 is just 1. So at this point, to see if you know how to do it on your own, you should press pause, try a few, and then check your answers. And you hit play. So again, press pause, and by the time you hit play, you'll be able to see your answers. Okay, let's check to see how you did. Here we should have x times x will give us x squared, and 6 times negative 6 will give us negative 36. Here, check to make sure you have y and y, 10 and negative 10. Here, make sure you have the 3's in the first term. It does matter what order, because 3 times 3 is positive 9 only. And then I have minus 3d and plus 3d would combine to nothing. But here, positive d times negative d gives me a negative d squared. It is not okay to have these backwards. The square root of the first term must always come first, followed by the square root of the second term in each factor. Here, check to see if you have 9h and 9h to get that 81h squared, and then 5 and negative 5. Here, check to see if you remembered this c squared. It's not just c times c, it's c squared times c squared that would yield c to the 4th, and then 15 and negative 15. We had answered number 7 already, and check the hardest one on the page. 3y times 3y would give us 9y squared, and then check to make sure you didn't forget this exponent either. 10z squared and negative 10z squared would give us negative 100z to the 4th. So now you should be able to factor a polynomial that has the difference of two perfect squares. By tomorrow in class, we will continue to differentiate between both methods, GCF and dots, and you'll know when to use each one. Thank you for watching.